And hello everyone. In this video, I want to talk about my fluid mechanics libraries written in Rust. And how I'm going to do this is basically, I'm going to use NeoVim, or older version of NeoVim installed through Chocolatey on Windows to explore Rust. So you can see I'm nerd 3, I've split my window panes up. And also, if you want to know what commands I'm using, don't hesitate to look at the bottom right-hand side, and where I'm using this code called Karnak, which is it looks like a free and open source thing on Windows, which is pretty much like screen key on Linux, so that when I type the things, it will be on the bottom left. Now I'm not really sure how to put it towards the center, but if you don't, but I guess it's also in a convenient place, because if you don't like looking at all this screen key stuff, what I'm typing, then it will be sort of out of your way. Okay. So basically what I've done so far is to git clone the fluid mechanics Rust library. I'm not going to go through how to do that. And I also have Cargo Watch installed on my in Cargo in PowerShell, and it's currently running my main function over here. And over here, what you can see that is that it's calculating some things. These are just some example functions, very sloppy tests, so-called tests I've written that I've not used the Rust test code to do it, but yeah, that's what I did so far. Okay, I'll probably want to work a little bit more on the documentation, but other than that, yes, it is what it is. Okay. So I didn't spend so much time documenting it, and now I want to document it. And yeah, here we go. So the first thing to do is, what's this library about? So this library is about, as the name suggests, it's fluid mechanics libraries. Okay, it is meant to help you calculate pipe friction losses and etc. But written in Rust so that you can get it calculated as fast as possible. So fluid friction factor. Yeah, friction factor. So here is what we are talking about. I can, of course, it's relatively easy-ish to calculate, and you can go online and you can check things like engineering toolbox, and you will be able to calculate the friction. Oh, this is the wrong friction factor. Moody diagram, Moody diagram and Colebrook equation. So this is what you're looking for actually. You want to calculate these things. So how I actually do it in Rust is, or at least this iteration, is to actually use Churchill Correlation. Okay, so this is a Churchill Correlation, which is a friction factor. And of course, you go to powderprocess.net, and this is what the equation looks like. So the friction factor here, I believe, is the Darcy friction factor, which is different from the Fanning friction factor by a factor of 4. Yeah, so it's 4 times the Fanning friction factor, and you will see that the two terms here, one is A, one is B. The B term, these terms here are actually help you to calculate more or less like this part of the curve towards the right hand side, the turbulent side, whereas the term on the left hand side here, this actually is the laminar part of the curve. And you will see that if Reynolds number is very small, A and B actually become very, very large, and this term on the right hand side becomes negligible. Okay, so that's what we are using here. Okay, so I'm just going to copy and paste it here. Okay, and if I'm not wrong, I have to use this, and I want to use the LSP install server. I want my markdown to actually do well. I'm using a Vim LSP, which is not the Lua LSP done in NeoVim. Excuse me. It's not the Lua LSP done in NeoVim, but it gets the job done. Okay. And it's mostly compatible with Vim as well. Okay. So here we are. So I'm going to copy this here. Okay, VN $, cut, paste it here, and Churchill Friction Factor. So I'm going to put this on the next side, write it. Okay, and this is on my develop branch. So You may or may not see this. Okay, so yeah, once you get this Churchill friction factor, you should be able to calculate friction factor given two things. One is this relative roughness, or what I like to refer as the roughness ratio. The other thing is, of course, the Reynolds number. So there are two input parameters, both are dimensionless. And once you put them inside, you will be able to calculate the Darcy or Moody friction factor. And that's exactly what I'm doing in my code here. You'll see that this function B and this function A here, they are exactly to calculate the A and B that you see over here. The A and B things you see over here, 2.457, logarithm, natural log of 1 over this thing here, 7 over RE. So how I do this in Rust is as follows. Okay, I literally have a variable called 7 over RE, 7 over Reynolds number. So this is the 7 over Reynolds number term. Okay, I power it using the powerf function to 0.9. So that's to the power 0.9. And then I have a roughness term, which is 0.27 times a roughness ratio. So as I say, I just use this roughness ratio, and this is dimensionless. So I'll leave it in a float 64 format. Any dimensionless number, I will try to leave in float 64 format or double format, and that's what you get. Yeah, the roughness. Okay, so of course I need to take a logarithm of the inverse of this. So what I do here is that I'll have a log fraction. This log fraction is 1.0 over the roughness term plus the Reynolds term. So 1 over these two terms together. Okay, and then I have this log fraction, and then I have this inner bracket term, which is 2.457 times the log fraction, which you take the natural log of. Okay, so this log fraction here, this inner term here, you take the natural logarithm of it times 2.457. So this inner bracket term, I take it to the power 0 of 16, and then I just return A. So this is what A does. Okay. Same thing for B. B is relatively more simple. 37530 over Reynolds number to the power 16. Okay, 37530 as a float 64. So this one you can kind of ignore it, just to tell the compiler that this number is supposed to be a float 64. I'll power it to 16. Okay, the denominator will also be powered to 16. So it's 37530 to the power 16. Reynolds to the power 16. Then that's the denominator, Reynolds to the power 16. So I divide one by the other, I get B. Okay, that's relatively straightforward. Okay, so next thing I use to calculate is this thing called the Churchill inner term. So I have my A and my B. And then on the left-hand side here, I said, yeah, this is more or less the laminar term. And this on the right-hand side is like the turbulent term. It's responsible for the turbulent part of the equation. So I call this the turbulent term. Okay, 1 over A plus B to the power 1.5. Okay, and then these two together is what I call the Churchill inner term. Okay, because you have an inner, this large square brackets, which are to the power 1 over 12. Whatever's calculated inside, I just call it the inner term. You can see I have an 8 over RE, and I call this the laminar term. I'll call this the laminar term, which is 8 over RE to the power of 12. And I have the A term, which is this A, and B, the B term, which is B, of course. And I have to calculate the actual values based on the Reynolds number and roughness ratio. So this thing, I'll just call it 1 over A plus B inverse, because I have 1 over A plus B. Then this turbulent term is the A plus B inverse to the power of 3 over 2. So this is what the 3 over 2 part here, which is 1.5. Okay, and then I return the laminar term plus turbulent term, which is this laminar term here, plus the turbulent term here, to get the Churchill inner term. Okay, so once that is done, you will come to this part. So let me just yeah, I'll just explain this part. So how does this code work here? How does this code work here? You will see a lot of things over here, so-called panics. These are panics. Well, the reason why I wrote panics here is because it basically tells the code to throw you an error if something goes wrong. And this is a sort of carried over because I was translating all this code from what I wrote in C#. In C#, I wrote a lot of exceptions to catch invalid values. So the direct translation for that is just to throw panics. May not be the best way, but it's what I've done, and so far it works. Okay, so but we'll skip this part first. We'll skip this part first, and we'll go straight here. Okay, so what I'm doing here is, firstly, I'll get this inner term done. I have an inner term. Okay, I make the inner term first. So I have this inner term. I need to take it to the power of 1 over 12. So that's what I'm doing in the second part. So I call this the power term. Okay, the power term is the inner term to the power 1 over 12. Next thing is to return the fanning friction factor. So fanning friction factor is 2 times the power term. Here it's over here it's 8 because it's a Darcy friction factor. So I did not multiply it by 8. So I just return the fanning friction factor, and whenever you want, if you really want, you can call the Darcy friction factor. And what I'll do is that I'll just return 4 times the fanning friction factor, and that will be the Darcy friction factor. And of course, if you want to use the Moody friction factor, some people call it the Moody friction factor. It is also like pretty much the same as the Darcy friction factor. So I just left it there for convenience. If I'm not wrong, Darcy and Moody are more or less like the same things. Okay, so let's talk about the panics. And what are these panics called? What is this doing? Okay, so this panic button, the panic thing here is that, all right, I'm catching invalid values. For example, like if the Reynolds number is 0, we are going to have problems. Why? If you take a look at this 8 over RE term, or even anything over RE, if anything you take it, you divide by 0, you're going to have a issue, right? You're going to have a issue here. So this fanning friction factor cannot deal with Reynolds number equals to 0. So I will pretty much say, if Reynolds number is less than 0, I will complain that the Reynolds number is 0, don't calculate. Okay, throw an error. Okay. Second thing here is that, okay, this code doesn't this friction factor does not handle Reynolds number below 0. Okay, it handles Reynolds number more than 0, and if anything less than 0, this Churchill friction factor will not be accurate. So I'm going to say if Reynolds number is less than 0, throw an error. So this is what this code here is doing. Third, last but not least, I will also want to make sure that the roughness ratio here, it is a valid value. It has to be a valid value. Okay, so yeah, so if the roughness ratio is less than 0, this is like not a physical, does not make sense at all. So I have to make sure that if you supply this wrong number, it will throw this error. Okay, so that's the idea here. Okay, and that is pretty much it for this part. Okay, so very simple Churchill friction factor. I'm not going to go too much into detail because very much further. Yeah, it is what it is, and this is the backbone of the entire code. Yeah, it's based on the Churchill friction factor. Of course, there are better ways. There are other ways of doing. There are other ways of doing things, but as it is, this correlation actually works pretty well. So I'm not going to change it. All right. So that's all. See you in the next time. See you next video.